Okay, chapter 4, we move on to dynamics and Newton's laws. Newton's laws are universal. They work for the whole universe. So you definitely want to be aware of those. Uh, Newton is the founding father for classical mechanics. So definitely those laws, uh, those laws apply everywhere. It's not just mechanics that you see. Once you go to electricity and magnetism, guess what? Motion of electrons and protons is still governed by Newton's laws. So it's really important that you understand them and you're capable of solving problems based on Newton's laws. And the first big parameter for dynamics is, of course, a force. We haven't discussed the reasons for motion yet. Now it is time to introduce uh, you to force, because forces are the main reason for getting acceleration. So we just said, oh, it was a free fall acceleration. And now we say, hey, there is a force of gravity that actually creates that free force acceleration, the free fall acceleration. So this is the next step. And you have to become familiar with all sorts of forces that we're about to discuss and understand that forces help you to get to acceleration. And once you know acceleration, you go to kinematics equations and solve for velocity, time, position, everything that we solved problems for before we discuss dynamics. So force is a vector. That means two things, magnitude and direction. And for force, you can think about a push or a pull on a certain object. We're still talking particles and no air resistance for most of the problems. And force is said to act on an object, and force will change object's velocity. And change in velocity, that's what we call acceleration. So force changes velocity, and therefore force creates acceleration. Forces have units. Units are newtons, and you can measure those newtons with a spring scale. Like the more you pull that spring, the more units you see showing on the meter, Newton meter, dynamo meter. But the point is, forces are just another, just another parameter that has units, has magnitude and direction, and you can easily solve for, say, missing forces, and from there go to acceleration and solve kinematics. Okay, Newton's laws of motion. The first thing to keep in mind is we can't really use them for speeds close to the speed of light. Every time you travel at a fraction of the speed of light, like close to speed of light, say half of the speed of light or 20% of the speed of light, you have to introduce special relativity coefficients for the equations that we're about to discuss, and Newton's laws will not give you the exact answer. They must be updated to general theory of relativity. And then once you go deep into subatomic particles and then quantum mechanics, some of those interactions have greater forces that will, that will be more prevalent compared to electromagnetic forces that we discuss in electricity and magnetism class. And gravity would be the least of all the forces to consider. So if you decide to go to quantum mechanics problems, then Newton's laws would not be very helpful. So you can see that the cases are really super duper special, and we normally don't deal with those cases when we solve just basic engineering problems here on the surface of the Earth for everyday life. So Newton's laws of motion are helpful for everyday situations. You definitely want to consider dynamics equations for normal engineering problems. And the first law is very simple. Honestly, it's not Newton's law, it's Galileo, who definitely takes like 90% of the credit for it. And Galileo is famous not just for this, but also for his Galilean moons, the telescope that he used to observe and prove that we have heliocentric model, the sun is in the center, not geocentric model when Earth is in the center. So technically, it's Newton's first law, but keep in mind that it's actually Galileo's law. And the first law says that if no net external force acts on a system or an object, then there will be no change in velocity. So the short version would be no force, no change in motion. And if there is a force that is not balanced by other forces, then you will get some change in motion. So first law, pretty much common sense. The absence of forces will not create any change in velocity. You can't get any change in velocity if there are no forces acting on an object, or if forces are counterbalancing each other, then also no change in motion can be observed. And I keep on saying net force, net force, net force. The net force is just the vector sum of all the forces that you can think of for a certain system. So it's not just, okay, simple example. You are sitting on a chair, and there's definitely gravity pulling you downward, right? So there's definitely a force that acts on you, and that should create some kind of a change in motion for you. But you experience no change. You just keep on sitting still because there is another force, the normal reaction force from the chair on your body, that counterbalances the gravity and makes the net force zero. So even though there are multiple forces acting on your body right now, there is no change in motion because the net force is just zero. Gravity is balanced by normal reaction force. So it's not just one force that you think of, it's all the forces combined. That's the net force. That's what you have for the second Newton's law and all the calculations that we're about to do. So if there's no net force acting on the object, no change, and you will keep on moving in the same direction with the same speed, or you will stay at rest if you were at rest, so no change in motion. And it's funny how this first law helps you to understand what's going on with spacecraft once you launch that spacecraft into space and it's far from any massive objects, that spacecraft will just move on over and over and over again for forever, because there is no friction, there is no air resistance to slow it down like for satellites that orbit the Earth. And if it stays far from gravitational, strong gravitational fields, it will just keep on going through space up until it hits some kind of a gravitational field or will collide with some other objects. So no fuel is needed for spacecraft to get through space because of the first Newton's law. No reasonable forces around, no change in motion. So units are newtons. Newton is kilograms multiplied by meters, divided by second, and by second again. And just by looking at the dimensions, you can say that force is mass times acceleration. This is the second Newton's law right there in your dimensional analysis. So acceleration is proportional to the force, directly proportional. And you can see how other parameters, other units can be represented as a combination of base units. Remember, we have base units, kilograms, meters, and seconds, and other units are just combinations of those base units. So forces are vectors. That means magnitude and direction. That means you have to add or subtract forces as vectors. So it's either geometrical approach with triangular or parallelogram methods, or you do things by components like we did in chapter 3. So exactly same procedure, finding the components, doing the Pythagorean theorem, and defining the reference angle with respect to a certain axis. Exactly the same process as before in chapter 3. And of course, for direction, you want to show those forces on the sketch. Okay, so how do you add vectors? Remember, option A, not good because it's the other diagonal. Remember, for parallelogram method, everything starts from the same point. So you have to use the other diagonal. That's why option A is not good. Option B, same thing. It's the other diagonal. Everything should start from the same point. Option C is good. It's your triangular method. Second vector plus the first vector, that's the vector sum. That's the correct triangular method. Option D, also good triangular method. First vector plus the second vector, that's the vector sum. Option E, that's the correct way to do parallelogram method. Everything starts from the same point. You can see that you have the origin, your x component, your y component, and that's your total vector sum. And option F is not good because the diagonal is correct, but the direction is opposite to the correct one. So F is not good because it's in the opposite direction. So remember, we did this for velocity vectors, for acceleration vectors, for position vectors. Now we have to do it for forces. Forces undergo the same procedure as other vectors. Now, remember reference frames. You have X and Y axis to show and to define. And it turns out that only inertial reference frames are good for Newton's laws. Newton's laws will not work in a non-inertial reference frame. Now, of course, your question is, what is an inertial reference frame? What's so special about an inertial reference frame? And the answer is simple. This reference frame cannot accelerate, okay? Your reference frame might be just still, just not moving at all. Your reference frame can actually move with constant velocity. That means the same direction and same magnitude, and no change. And all of those are good for Newton's laws. But once your reference frame starts accelerating, it is not an inertial reference frame anymore. And you have to, convert it to the one that is not accelerating. Otherwise, Newton's laws will not work. And you might say, hey, Earth spins on its axis. We have day and night because of that. So Earth has that centripetal acceleration that we are about to discuss soon. So Earth is accelerating. And I would say yes. Earth technically is a non-inertial reference frame because, yes, there is centripetal acceleration, and yes, Newton's laws are not valid, so we can't technically use them for our planet, for the surface of our planet, but we found a way to update some of the values so that we can actually ignore the spinning of Earth and consider it just a still object. And in order to use Newton's laws for our planet, for daily calculations, we have updated the small g, the free fall acceleration. Remember, free fall acceleration is considered 9.81 for your calculations, which is actually not the truth value. The truth value is 9.83, which is not a big deal, not a big difference, but still, it's a difference. And in order to, take care of spinning Earth, we modified the free fall acceleration, which includes the mass of the Earth and the size of the Earth. And if you consider 9.81 for the free fall, then you say Earth is an inertial reference frame, and you can use Newton's laws with that value for the free fall. So ground is an inertial reference frame because we have modified the small g value from 9.83 to 9.81. Yeah, that's exactly what this slide is all about. So Earth rotates, and we updated the value for small g, and with that adjustment, you can consider the Earth not spinning and just use Newton's laws for all your calculations. Okay, now mass. First of all, it's not the same as weight. Every time somebody asks you what's your weight, you have to be careful, because weight is a force, and forces are measured in newtons. Now you know that newtons are the units for forces, so be careful. Next time you go see a doctor and he or she asks you for your weight, do not tell them pounds or even kilograms, because that's not weight. Kilograms are mass, and weight is a force. Okay, so for mass, think about a parameter that is just a coefficient between the net force and the acceleration that this force creates. So the more mass you have, the more force is needed to gain a certain acceleration. You can think about some kind of a resistance to a change in motion, if you will. You might hear the word inertia for the same reasoning. Anyways, mass is just a coefficient. It's a scalar. There's no direction for mass. It's just a number of kilograms that the system has. And because of mass, you have a certain resistance to a change in motion. And once again, weight is a force, and force is a vector. So for the weight, not only it's going to be newtons, but also it will have direction. So mass and weight, not the same thing. Remember, we had velocity and speed was just a scalar, no direction, and velocity was a totally different definition, and it was also a vector. So direction and different units. Be careful, mass is not the same as weight. Yeah, that's what this slide says. Weight is force. You fly to the moon. Your free fall acceleration on the moon is 1.62 meters per second, which is 6 times less than we have here on Earth. So the weight will change. You'll weigh 6 times less, but your mass is still the same because you will still be made of the same amount of atoms and molecules that create, the mass that your body is made of. Okay, second law, it's your connection between the force, the mass, and acceleration. The formula is very simple. I'm pretty sure you've heard about F equals ma. However, Newton never said that. Newton never defined the second law as F equals ma. Newton was genius enough to consider the case when mass is not constant. If mass is constant, yes, you do get ma. But let's say mass changes. Let's say you have a rocket, and you know how rockets, it's like 90% it's just fuel, and 10% is the load that you want to deliver to, say, space station. So that rocket will lose 90% of its mass. Once it's fired and it's going to space, it's going to lose about 90% of its mass. Can you say F equals ma for that process? Not anymore. Your mass is going to change. So Newton said it's the change in momentum with respect to time. And we'll discuss momentum later. And momentum takes care of both mass and velocity. If mass changes or velocity changes or both parameters change, then you have a change in momentum, and that's how you define the force. That's what Newton said for real, and this is your true second Newton's law. But for our simple introductory level general physics class, you say F equals ma. Make sure you draw those vectors. Make sure you say net force. It's not just a single force, but all the forces combined as vectors. And you can solve problems on dynamics with this statement. Okay, it is time for the first video, mass, acceleration, and force, for you to, separate those definitions and see how they're connected. Let me load the video. And do the share menu, share, media player, share sound. Share.
When you're first learning about motion, sometimes the difference between velocity and acceleration is pretty confusing. I like to keep track of them by thinking about the velocity as telling me what the object is doing, and the acceleration is all about what the object is about to do, what it's going to do next. I have a ball here in my hand, and I'm going to exert a force on this ball. At the moment, the force is exactly equal to the force of gravity, but in the opposite direction. So I push up on the ball, and gravity pulls down on the ball, and then it just sits there. If I push up harder, the ball moves up, and if I push down not as hard, the ball moves down. If I toss the ball in the air, as soon as it leaves my hand, the only force acting on the ball is gravity. Gravity pulling it downward. So I toss the ball again, and I want you to think hard about what's going on at the top of that toss. Right there at the top of the toss, the velocity of the ball is 0. It's stopped. That's what it's doing. It's just sitting there at the top. But what is it about to do? Well, it's about to fall. So the acceleration must still not be 0. So right there at the top, the velocity goes to 0, but the acceleration stays the same, so the ball comes back down again. It might seem kind of strange to you that an object could have 0 velocity, but not 0 acceleration. I have another demonstration for that. Here I'm standing, just standing still. If I have no acceleration, I will continue to just stand still. I don't go anywhere. I never get started going anywhere because both my velocity and my acceleration are 0. In order for me to go somewhere, I have to actually start moving. There has to be a moment when I'm about to go. So I push back on the earth pushes forward on me, and I have an acceleration that's sending me forward. And then I have a velocity. So I have a non-zero acceleration that leads to a velocity. That acceleration is telling me what's about to happen. The force, the mass, and the acceleration are all related to each other. So when I exert a force on an object, the acceleration that it experiences depends on the mass. Here I have a little car on this track in front of me, and I can push on this car with different forces. The car has just one mass. It's the mass of the car. If I push on the car very lightly, then I'm going to expect it to accelerate, but not much. And it does that. If I push on the car harder, what do I expect? I expect it to accelerate more because it still has the same mass. So here now I'm going to push on the car harder, and it accelerates more, just as I expected. To figure out how the mass matters, we need to have a way to hold the force constant. And these cars come built in with a way to hold the force constant. They have a little rod stuck inside them with a spring, and if I push this button, the rod shoots out, and it always shoots out with the same force because it's loaded from a spring instead of from me pushing it. So I'm going to push that rod back inside, and I'm going to go ahead and set it against this stopper, and I'm going to push that button. And we expect to see the car accelerate that direction. So let's see what happens. It accelerates pretty quickly. That rod exerts a pretty big force on the car. Now I'm going to push this back in, and I'm going to add some mass to the car. So now the car is going to be heavier. Okay, it's going to weigh more, and it's going to have more mass. So I put the mass in the car. What do we expect? What we expect is that because the car is more massive, that same force is going to accelerate it less. So let's see what happens when I push the button. The car accelerates less. The force, the mass, and the acceleration are all related to each other. A bigger force on an object of the same mass produces a bigger acceleration. The velocity and the acceleration are two different things. The velocity tells you about what the object is doing, and the acceleration tells you what the object is about to do.
Okay, so back to presentation. You can see that mass is connected to acceleration and the force. Acceleration is not the same as velocity. Well, we figured that out in previous chapters as well. So the experiment shows you that the more the mass, then you need more force to get the same acceleration. And if it's lesser of a mass, then less force is needed to do that. Okay, now the third law. The third law is a fun one, because even if you understand the words, I'm pretty sure you've heard for every action, there is an equal and opposite reaction. And then someone starts asking you questions about the third law, connections, and then you fail it miserably. And we'll do the same thing here. So third law is still tricky. It's not enough to just remember the words and just say the words and that's it. You have to really get into it and understand what's going on. I'll try to explain that. So for any kind of force that you can think of, say action force, for any kind of action, there's always going to be there a reaction force. And reaction means it's going to be opposite direction. It's always opposite direction. And that reaction must be exactly the same. Say you hit the desk with a hand. If you hit it just lightly, you say ouch, but it's not gonna really hurt much because the force that you hit the wall or the desk, it's not a large force. But if you hit it really hard, you say ouch, it really hurts now because the action force was quite large. So first of all, understand that subscripts are not the same, because if action is hand on the desk, then reaction is going to be desk on the hand. So hand on the desk, desk on the hand, we already have some things to worry about. You should always read the question carefully. Is the question about how hard you hit the desk with the hand, or is it how hard the desk reacts to your hand? So subscripts are important. Is it the action force, or is it the reaction force that is in question? And then you can see the diagram shows that vectors are opposite. So you have two different forces, and they are the same magnitude, but direction is opposite. You hit the wall and wall hits you. Gravity from Earth pulls on you, and you pull on the Earth. And fun fact, the Earth will pull you with exactly the same force that you pulls on Earth. Forces are the same in opposite direction. Keep that in mind. So this is your action-reaction pair of forces. So B on C, C on B. And you see there is a negative in front. Negative means what? Direction is opposite. This negative takes care of the direction. Say you are in a skating rink and you push against the wall. So you push on the wall, and wall pushes you in the opposite direction. Have you ever tried doing roller skating or skating in general? I'm pretty sure you've noticed you push forward and then you go backwards. In fact, if you think about it, you can walk on the surface of the earth only because you're actually pushing backwards. Try to walk on ice. What's going to happen? Not much is going to happen because ice will not provide any friction. You will not be able to push against the ice. But if you're on the solid ground, wearing some shoes, you push backwards and the earth propels you forward. So direction is opposite. and action-reaction magnitudes are the same. So the stronger you push backwards, the faster you're going to go forward. That's how you can run. For running, what matters is how strong you push backwards. For rocket going upward, why does the rocket go up? Well, the rocket goes up because something's going down. What is going down? Well, you can see on the diagram, expelled gases, expelled fuel that you burn in the chamber, all those gases go down. And only because gases go down, the rocket goes up. It has nothing to do with, air resistance, air support of any kind, none of that. It's only some kind of a force that is action, and the rocket goes backwards as reaction. The rocket does not need to push against anything. It's only the gas that you burn in the chamber and gas expelled downward that propels the rocket upward. So here is the question of the day. We know that the moon orbits the Earth, right? So the Earth pulls on the moon with gravity, and that's why the moon is orbiting the Earth. It's only here because there is gravity between the moon and the Earth. Now, the question is, how do you compare the gravitational forces between the moon on the Earth and the Earth on the moon? The question is kind of obvious, especially if you're familiar with the third Newton's law. Right away, you say forces must be the same because Newton's law says that. And if you say the moon pulls less because the mass is less or the size is less, then that violates the third Newton's law. So you have to remember that forces must be the same. Third Newton's law only makes sense when action is exactly the same as reaction. The Earth pulls on the moon exactly the same as the moon pulls on Earth. The sun pulls on the Earth exactly the same as the Earth pulls on the sun. Otherwise, the third Newton's law is not good. And trust me, it is good, it is valid. And the question might be, okay, if the forces are the same, how come the moon goes nuts around us and we're just sitting still? Well, the answer is the second Newton's law. And second Newton's law says what? Forces are on one side, and then you have mass times acceleration on the other side. And if forces are the same, but masses are different, then you have different accelerations. So what do we have for Earth versus the moon? Earth has much more mass. Therefore, it must have much less acceleration so that the force is the same. For the moon, what do you say? Mass is less, but acceleration is much more so that the product is the same as we have for Earth. And because of acceleration being much more, we have the moon orbiting the Earth, not vice versa. Same thing for the Earth versus the sun. What do we say for the sun? Well, it's called solar system because the sun takes 99% of all the mass. Mass is enormous. For the sun, mass is everything. So what do you say for acceleration? It's barely there. The sun is barely wobbling. Like it's not sitting still exactly, but it's a very, very small acceleration. Now, for all the planets, including Earth, what do you say? Mass is very small. So acceleration is very large. And that's why all the planets and asteroids and everything else comets, you name it, evil aliens, everything orbits the sun because of this enormous acceleration. And forces are the same. So forces are the same, but masses are different, so acceleration is different as well. This is the essence for the third Newton's law. Let's watch a video, laugh at those guys who can say the third Newton's law but still can't say what's going on, and keep the truth in your mind. Newton's third law. Let's do a new share.
There are a lot of misconceptions out there, and this is a video about one of the most common ones. So I went around asking people what makes the moon go around the Earth, and they told me,
the Earth puts a gravitational force on the moon.
but does the moon put a gravitational pull on the Earth?
Pull on the Earth? Yes, it does. Hence we have tides, etc.
The moon pulls on the Earth too. It affects like the tides and women and stuff. It does. Very powerful, this thing.
Does the moon pull on the Earth?
Probably that as well, yeah.
So what I want to know is how does that force that the moon exerts on the Earth, how does that compare in terms of size to the force the Earth exerts on the moon?
Well, I'm no scientist, but I think that one would be more powerful than that one.
It's got a greater force coming from the Earth because it's a greater mass.
Because the Earth probably has more mass.
Because it's a bigger mass. I thought greater mass is equals more force.
Does the moon pull on the Earth?
Yes, but a lot less.
Yeah, not as much as the Earth pulls on the moon.
Yeah, but a little bit.
But not very strongly.
Yes, but much, 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 much smaller.
Because of its mass,
less
its
mass.
size.
Because it's smaller, it's much smaller than the Earth.
Because it's smaller.
Because it's small.
Allow me to let you in on a little secret. Everyone got it wrong. The force that attracts the moon to the Earth is exactly the same size as the force that attracts the Earth to the moon. So what's going on here? Why did everyone get it wrong? Well, I think it comes down to cause and effect. The effect of the force on the moon is quite clear. The moon goes in circles around the Earth. But the effect of that force on the Earth is basically negligible. The Earth barely wobbles at all. So people interpret this negligible effect as indicating there's very little force affecting the Earth. But that is forgetting the third key piece of the puzzle, which is inertia. Inertia is the tendency of mass to maintain its state of motion. Since the Earth has a greater mass, it has a greater inertia, and so even with the same amount of force on it, it doesn't accelerate that much. Now the funny thing is, many of the people I interviewed could state Newton's third law, which is every force has...
Oh, an equal and opposite reaction.
Something about Newton's law doesn't seem to fit into that. You're good at this.
Which Newton's law are we talking about?
The whole equal and opposite force thing. Yeah, that one.
So tell me what you're thinking now.
Well, one would think that if the Earth is putting a force on me, I would be putting an equal force upon it.
So why didn't they apply it to this problem? Well, I think they may have memorized the words, but not really believed Newton's third law in their core. Did they really feel it in their spleen? I don't think they did. So, allow me to try to convince you, all of you, spleen included, that Newton's third law really is true. Let's consider two objects. Initially, they have the same mass, 1 kilogram each. So obviously, the gravitational force of attraction must be the same on both of the objects. Now let's add a second kilogram to the first object. The force on the second object will now be twice as great because that 1 kilogram is attracted equally to each of the kilograms in the first object. But what is often forgotten is that new kilogram is also attracted to the second object, meaning that the total force on each object is still the same. They're attracted to each other with an equal and opposite force. we could add a third kilogram and we would find the same thing. The force on both objects is still the same, even though the object on the left has 3 times the mass of the object on the right. So we can see that no matter what the mass, any two objects will have the same gravitational force towards each other. Can you feel Newton's third law in your spleen now? It should settle inside you and become a part of you.
Okay, so back to presentation. And back to some morals. Forces are the same in magnitude, opposite in direction, and masses can be different, accelerations can be different, but the product between the mass and acceleration should give you the same value as your action or reaction. Mass goes up, acceleration goes down. Okay, now the weight. So what is a weight? It is the force exerted on something by gravity. If we don't have any vertical acceleration, then the acceleration to think of for the second Newton's law calculations would be the free fall. So small g times the mass. This is the weight that you can think of. Once again, if no other vertical accelerations are present. So next time you go visit a doctor and he or she asks you for your weight, what do? You have to forget pounds. There's no pounds here. We have System International, and for whatever the pounds you have to cut it in half. Say for 150 kilograms, that would be like 75 kilograms, and that would be the mass. And then you have to multiply your mass by the small g. And small g on Earth is 9.8. You did the lab, and we discussed it before. So free fall accelerations like 10. 10 times the mass, 10 times 70. That gives 700 newtons. Okay? So your weight is not some number of pounds, and it's not even kilograms. Your weight is a force, and it must be in newtons. So you tell your doctor that your weight is, 700, maybe 800, depending on the mass. And don't you say newtons right away. Just say the number and watch the doctor's reaction. If doctor says, what the hell is that number? Then that doctor probably doesn't know basic physics, basic science. I wouldn't trust that doctor. I would find another one. But if the doctor says, oh, I get the joke, I get that you know what the real weight definition is, then it's probably a good doctor. At least that doctor knows System International and knows how to use forces versus masses. So mass in kilograms multiplied by small g. Once again, you go to the moon, your mass is still the same number of kilograms, but g is 6 times less, so your weight would be 6 times less. So no diet, no exercise, and boom, your weight drops 6 times. Pretty cool, huh? Yeah, no vertical acceleration. If there is a vertical acceleration, then you have to do some adjustments, and accelerating elevator is not the best way. You will be experiencing either overweight or underweight. So your weight should, if you're measuring your weight, you don't want any extra vertical acceleration. So here is an object, the Lincoln's monument at rest, sitting on the table. Why is it at rest? Because the force of gravity coming from Earth, acting on the object, is counterbalanced by what we call normal reaction force from the table, onto the monument. So monument pushes on the table, and table reacts back on the monument. So all the forces on the object combine together. One is, say, -5 newtons, the other one is +5 newtons, because one is up and the other one is down. You add them up as vectors and you get a zero vector, you get zero net force. So no acceleration. That monument will be sitting on the table, for forever until you hit it from the side, or the table will collapse for some reason, or the gravity will disappear for some reason. Yeah, so normal force. By the way, yeah, the word normal means perpendicular. So normal means perpendicular. And perpendicular to what? Perpendicular to the surface that your system leans against. So the monument is sitting on the table. That's the surface of a table. And normal force is perpendicular to that table. Okay? So if the table would be slanted, then the normal force would be slanted too. If the table is not horizontal but vertical, the normal force would be horizontal. So normal force perpendicular to the surface that your object leans against. So this is your diagram to solve dynamics problems. That's the block of something sitting on the table, and two forces act: gravity, normal force. Instead of a block, you can draw a point because we're still talking particles, and show normal force upward, gravity downward, x and y axis. That's the setup. That's the, yeah, don't forget the vector notation for forces. See, you have normal force with vector notation and gravity with vector notation. Instead of F sub g, you can just say mg. That's fine. That's what I like to do. So mg, small g, and the vector on top of g, because small g is a vector. You can do that. So let's find normal force for a block resting on its horizontal surface. And there is a vertical acceleration shown here. So if there is a block resting on a surface, you have two forces. You've got gravity. Gravity is always there. You should always draw gravity right away, because if we have Earth, something's on the surface of the Earth, and Earth will pull on everything with its gravity. And then normal reaction force, it's perpendicular to the surface. That's the surface. The normal force is perpendicular to that surface. And then there is acceleration upward. That's what's given. So let's find the normal reaction force. The first statement is the second Newton's law. Net force is mass times acceleration. And what is a net force? Net force is vector sum of all the forces acting on the object. So it's your normal force plus gravity equals to mass times acceleration. And then you have components onto y-axis. Y-axis is upward, positive direction is up. So normal force has the same direction. And if it's the same direction, it's a plus component, plus normal force. And gravity is downward. So what's the component for gravity onto y? Positive is up. Your gravity is downward, so gravity has a negative component. And gravity is just mg. Like I said, instead of saying F sub g, you just say mg. That's fine. And acceleration is up as well. If acceleration is up, then component is positive. You do have plus ma on the other side of the equation. So Fn minus gravity, mg, equals mass times acceleration. So that's what we have so far. Positive normal force, negative gravity, positive acceleration. So you solve for the normal force, you transfer gravity on the other side with an opposite sign. It was negative mg, now it's plus mg, plus ma. Factor out the mass, and you get mg plus a. So the more acceleration you have given, the more the normal force is going to be. If acceleration is 0, then you just have your normal weight with no overweight or underweight. So just mg. That's the simplest dynamics problem. You say the second Newton's law, you state all the forces, do the components, plus, minus. Later on, we'll do sine and cosine as well, because surface is not always horizontal or vertical. It can be slanted. And solve for what's missing. Normally, you would solve for acceleration. And once you get acceleration, the next question would be how much time it takes or how fast something's going to go. So that's kinematics. And with acceleration known, you can solve kinematics part as we did in chapter 3. Okay. Is the magnitude of the normal force greater, less, or equal if the block are going upward at constant speed? Constant speed is the key word. Constant speed means no change. Constant means no change. And if there is no change, that means acceleration is 0. Acceleration is 0. We go back to the previous example and get the same value for normal force and gravity. So it's equal to gravity. Constant speed, once again, is the key word because it clearly says no change. That means no acceleration. If we're going upward and speed is decreasing, remember, decreasing speed means signs of velocity and accelerations are different. You're speeding up when acceleration has the same sign as velocity, and you're slowing down if those signs are opposite. So decreasing speed means velocity is up, so acceleration has to be down. It has to be in the opposite direction, so that we are slowing down. If acceleration is down, see, it was up. Now acceleration is down. What's going to be different? Well, the left side of the equation is going to be different. It's not going to be plus ma anymore. If acceleration is down, you have a negative component, and your negative component will not give you a plus. It will give you a minus for the final equation. You'll get the opposite to the previous example, and mg minus ma, you subtract something from the original weight, you're going to get less of a value than the gravity only. So this time it's less than gravity. Okay, solving problems. For that, we need to define a few more forces. Specifically, tension. Tension is always there when there is some kind of a cord or a rope or a cable. Okay, every time you hear the word cord, rope, or cable, you have to say, oh, there's got to be tension in that cable or the cord. And the direction for that tension force is always along the cord. No exception. Later on, we'll discuss hinges, and for hinges, everything is possible. That's the main difference between a hinge and a cable or a cord. For hinges, anything is possible. But for cords, ropes, and cables, your tension force is always along the cord. and you say cord is under tension, that's what's going on. For now, for this level of physics, consider the cord being massless and unstretchable. It's going to simplify our problems dramatically. For solving, you don't have to consider any extra stretching, any unevenness in tensions. So, easy scenario. And for all of those pulleys that you see given, it's also massless and frictionless. We don't have to worry about friction within the pulley, which is also a big simplification towards problem solving. So no mass for the rope itself. And you can see how the third Newton's law is in place. You pull on one side of the rope, and then you're going to create the opposite reaction in the other side of the rope. So you pull on the rope here, and the tension that you create in one direction will create also a tension in the opposite direction on the object on the other side because of the third Newton's law. See, you pull down, and tension is created in the rope, and it's going to create the same tension on the other side as well. Those are assumptions. Why is it so? Because we assume it this way. So a classic example, two blocks are connected, and there is a rope, and this surface is frictionless. It's not going to be frictionless later, but for now there's just no friction whatsoever. Forget all the friction forces. You got two masses, and the question is, how fast will they accelerate? So what's the tension? What's the acceleration for the blocks? Let's see what we have in terms of the diagram, the so-called free body diagram. First of all, you have two different systems. You have block with capital M, the first, the massive block, and then the other block with a small m. So two different systems. And you'll get two different systems of equations. Let's discuss the first one. So the first one, yeah, capital M. Yeah, so for the first one, what do we see? We see the gravity acting on the big block, and this block is sitting on the table. And there is a surface. This surface provides normal reaction force, so F sub n, upward. And then the block is under tension because it is connected to the cord, and there is a tension force along the cord. For the second block, there is no table. It's just the cord that also creates the tension along the cord and gravity pulling on that block. So those are the forces. Don't forget to show accelerations because those are vectors, and you have to show all the vectors on your sketch. And it's now time to do the Newton's second law for each block. That's the general equation. And first one is the sliding block. What do we see? We have x-axis, and there is a tension force along the x-axis. And what do you say for other forces? See how this vector is perpendicular onto x. So what is the component of a normal force onto x? The rule says it's 0. Every time a vector is perpendicular on a certain axis, its component on that axis is 0. F sub n onto x is just 0. What do you say for gravity? Gravity is perpendicular onto x-axis, And every time a vector is perpendicular, its component is 0. So the only force acting on x-axis is the tension. So it's tension, and it's positive because it's in the positive direction, plus a 0 for normal force, plus a 0 for gravity. What do we say for acceleration? Well, mass is given, and acceleration is positive because it's in the same direction. It's the only force that creates acceleration. It's easy to figure out acceleration. Normal force counterbalances the gravity, and tension pulls with no counterbalance. So this is the net force. This is the force that propels the block across the table. So acceleration is to the right. So tension for the force, for the net force, and acceleration times the capital M for the mass. What do we say for y-axis? Well, for y-axis, you got the normal force, positive. You got gravity, which is negative. And then you got tension. See how tension is perpendicular onto y-axis. So what do you say for tension? Tension, if it's perpendicular onto a certain axis, its component on that axis is 0. So no tension onto y-axis. It's just the normal that is positive and the gravity that is negative. And what do you say for acceleration acting onto y-axis? Acceleration is perpendicular onto y-axis, so its component on y-axis is 0. Every time a vector is perpendicular to a certain axis, its component is 0 for that axis. So 2 equations for second Newton's law, dynamics for sliding block. Now hanging block, for x-axis, you don't get much. All the forces are perpendicular, so 0, 0. Acceleration is also perpendicular to x, so it's also 0. So you get 0 equals 0. It is a truth statement, but you can't really solve for anything from this statement. Now the y-axis is not 0. You got tension upward. You got gravity downward. So positive tension, negative gravity, and acceleration is down because, everything goes down. You have sliding block going to the right and hanging block accelerating downward. Acceleration is down. So if y positive direction is upward, then acceleration is opposite to that. So acceleration is negative. That's what you see here. Positive tension, negative gravity, and negative acceleration. Physics is over. The rest is algebra. Whatever is given, whatever is missing, you do the calculations, you do the substitution, elimination. Anything is possible. For this particular problem, you can solve for acceleration and tension force. You can plug in numbers, get the actual values, see how force is in newtons. Acceleration is still meters per second. And it's not free fall. Remember, it was free fall? Do we have free fall here? No, this block is connected to the other block. It's falling, but it's not free falling. So you can't say 9.8. Your acceleration is less than that because it has been slowed down by another block. Yeah, let's take a look at this one. We got 75 for gravity. Do we have tension more than that, less than that, or equal to gravity? Well, let's do the second Newton's law. Tension goes up, gravity goes down. Do we have any acceleration? No, it says what? Constant speed. Constant speed means no change in speed and no change in direction. So velocity is just also constant, means acceleration is zero. If acceleration is zero, the second part of the right side of the second Newton's law equation is zero. So the left part gives you T equals mg. So tension is exactly the same as gravity. So exactly equal to if it's constant speed. There's only going to be a different story if you have some kind of acceleration. But if acceleration is zero, then tension is the same as gravity. Yeah, what if it's moving upward and increasing speed? Remember, speeding up means acceleration has the same direction as velocity. So moving up, increasing speed, acceleration is up. Acceleration is up, it means acceleration is positive. So tension is still up, gravity is still down, and acceleration is positive. Solve for tension. What are you going to get? You're going to get mg plus ma. So you're going to get more than mg. And that means it's b is greater than. It's mg plus extra. That means more than mg. And if speed is decreasing, so upward and decreasing speed, that means acceleration is actually down because velocity is up and we are speeding and we are slowing down. So acceleration is opposite direction. So acceleration is negative for my second Newton's law equation. And you solve for tension, you see that it's going to be mg minus ma. So you're going to subtract something from the original mg value, and you're going to get less than mg, less than 75 newtons. That's the third option. And now friction. Friction is always opposite to the direction of the attempted slide. If you have some motion involved, then it's going to be kinetic friction. If there's no motion, then it's static friction. So two types of friction, static or kinetic. And good news, for both scenarios, friction is always opposite direction to the direction of motion or attempted slide. Once you figure out direction of motion, good news, friction is going to be opposite to that direction. Friction always trying to slow you down. How much of a friction do we have? It's a special coefficient of friction multiplied by the normal force. And for static friction, it can change from 0 up to this value. And for kinetic friction, it's just this value, as you see, equals 2, and kinetic friction, it's always the same value. For static friction, be careful, it's not exactly equal to. It can be less than that. For static friction, it can be the same as mu times normal force. Mu is the coefficient of friction, which you can find in the table in the textbook, and you don't have to memorize it. Oh, and good news, this is the only thing in this class that will not have any units, because you have forces on the left, forces on the right. Dimensional analysis says that this coefficient cannot have any units. So this coefficient is unitless, and the values are found in tables. So whatever is the mu, or you want to solve for mu, the only thing you have to keep in mind, whether it's static or kinetic. Do you see the difference? For kinetic, it's exactly equal to, and for static friction, it can be less than that. Yeah, you can see the diagram that shows you how it's static, 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 then boom, it's kinetic. So for static friction, you have a change in values, and once you hit to kinetic, once you hit to motion, let's say you want to push a table, a very heavy table. You push, and table doesn't move. And then you just keep pushing stronger and stronger, more and more force, and eventually you're going to push the table and it will start moving. That's the moment when it starts moving, and your static friction becomes kinetic friction. So no motion, and then boom, there is sliding motion for the table. So different values for static, same value for kinetic, but not more than mu times normal force. And a brief introduction to a slanted inclined plane. You see that there is an object on an inclined plane sliding downward. What do you see? You see gravity. Gravity is still downward. You see friction. Friction is opposite to the direction of motion. If motion is this way, then friction is exactly the opposite. And I want to point out that normal force is not up. Remember, normal force was upward every way here. Normal force was up. And for that Lincoln, this was up. It's not upward anymore. It is slanted. It's perpendicular to the direction of the surface. Surface is inclined, it's slanted, so normal force is also slanted. It's not exactly vertical. It's at an angle, but it's still perpendicular to the surface. This is the direction of normal force. And you can see that for this kind of a problem, you will benefit from switching from regular XY coordinate system, X is to the right, Y is upward, to the slanted coordinate system. It will save you some work for sine and cosine components. So try to, every time you see an inclined plane problem, make sure your X is parallel to the inclined surface and Y is perpendicular to the surface of inclination. Do not do regular XY components like you used to. We'll solve a few problems later for that. The lecture part is over. I'm gonna stop the recording and we'll do the classroom discussion after that.